So Fourier representation of periodic. So Fourier representation of periodic signal. So the representation of signals and system using complex sinusoid is called Fourier representation, and it is named after Joseph Fourier. So this particular guy, created this Fourier series, and what wonderful it is. We can analyze a signal in terms of frequency domain, and I explained you exactly why we need to, transform the signal from time domain to frequency domain and analyze the signal in frequency domain. Okay, so depending upon the nature of the signal, there are four distinct representation of the signals. Okay, first one, yesterday as I explained, your signal may be periodic, your signal may be aperiodic, then your signal may be continuous time signal, and your signal may be discrete time signal. So if your signal is continuous time signal and it is periodic, then you have to use Fourier series. Okay. Then if your signal is continuous time signal and it is not periodic, so periodic means which repeats, not periodic means it doesn't have periodicity. Okay, then you have to use Fourier transform, and your real life signals you use in most cases Fourier transform. Okay, then coming to discrete time signal, if it is periodic, you use discrete time Fourier series, and if it is non-periodic, you use discrete time Fourier transform. Okay, so it's just simple. You write this table: periodic, non-periodic, continuous and discrete, and see continuous if it is periodic, Fourier series, non-periodic, Fourier transform. That's it. Okay, now in this particular module, or this for today, I'm going to concentrate on continuous time periodic signal, which is nothing but your Fourier series, CTFS, continuous time Fourier series. So today we are going to see upon this thing and solve some problems with respect to continuous time Fourier series. Okay, now now if you take your Fourier series representation, you can represent in terms of trigonometric series, you can represent in terms of exponential, or you can represent in terms of harmonics. In mathematics, whatever you have learnt in terms of trigonometric series and exponential series. Harmonic, I don't know whether you have learnt or not, but since this is electrical engineering, we will take simplified one. We will take exponential Fourier series representation of continuous time periodic signal. Okay, so how can we do that? Let x of t be periodic with a fundamental period t. Then x of t can be represented by infinite series of complex exponential. But yesterday I told you we can represent the signal in terms of cos and sines, but this sir today he is saying in terms of complex exponential and is confusing us, right? So that might be the confusion which is running around your head. But you can say, if you can express cos theta is equal to half of e power j theta plus e power minus j theta, and sin theta is equal to 1 by 2j into e power j theta minus e power minus j theta. So this mathematical expression you have learnt in mathematics. So if I written in terms of exponential or cos, it's the same. So the definition remains the same. You are going to decompose a signal in terms of sine and cos, I told, Fourier series. But here I am writing as complex exponential. So if I write complex exponential or sines and cosines, it's same, because we can transform from e power j to cos or sine, or cos and sine into e power j, we can express it. Okay, so we have two equation with respect to your input signal x of t. One is the synthesis equation and another one is the analysis equation. Okay, so what is your synthesis equation? X of t is equal to summation k varies from minus infinity to infinity x of k e power j k omega naught of t. So this equation we have, I have explained you in the previous class while giving the intuition why we do that. So this expression x of t is equal to k varies from minus infinity to infinity x of k e power plus j k omega naught t. Please remember, so this is helpful in solving the problems. Then there is second thing which is known as analysis equation. So what is this analysis equation? X of k. So x of k is equal to 1 by t. So 1 by t integral 0 to t x of t e power minus jk omega naught of t. So what we are doing is we are finding them Fourier coefficient. So x of k is nothing but your Fourier coefficient. How do we get 1 by t integral 0 to t x of t e power minus jk omega naught of t? Okay, so these two equations you have to remember while solving the problems. Okay, here x of t has a fundamental period t. Because it's a periodic signal, it has a fundamental period t, and the fundamental frequency omega naught is given by 2 pi by t. Okay, then it is expressed in terms of radians per second. So x of k is called the Fourier coefficient. So whatever you are doing, x of t, you are converting into frequency domain, which is x of k. So x of t is your time domain signal and x of k is your frequency domain signal, and using this equation you are converting from time domain to frequency domain. Okay, so please remember these two formulas. Okay, now amplitude and phase spectra of periodic signal. So we have got our Fourier coefficient. So it has real part and imaginary part. So x of k is equal to a plus jbk. So what is the magnitude of this? Simple, root of a squared plus b squared. Then what is the phase? It is nothing but the angle. So theta is equal to tan inverse of b by a. So b we know, a we know. So we can calculate theta as tan inverse of b by a. So now if you plot this x of k with respect to k, then it is called as amplitude spectra. If you plot angle of k with respect to k, then it is called as phase spectra. So that is a major difference you have to observe. Okay, and k, it assumes only the integer values. Okay, whenever you're converting from time to frequency, so your time domain might be in continuous, but this frequency domain k, whatever you're converting, it assumes only integers, that is 0, 1, 2, 3, or minus 1, minus 2, minus 3. You can't have a value like 1.5, 2.5, 3.5. Okay, so they only appears at discrete point of time, and hence they are referred as discrete frequency spectra. Okay, now we will see the properties of Fourier series. Okay, in your syllabus it is not mentioned, but to be on a safer side, let me explain you what is this properties, because you will be applying these things in control system or digital signal processing, and that time you should not say sir did not teach you. Okay, so first one is linearity. So according to linearity in time domain, so if you can see here, 1 minute, let me make it bigger so that you can see it properly. Okay, okay, so linearity property. So if you can observe here, we have a1 x1 of t and a2 x2 of t. So if you add this in time domain, a1 x1 of t and a2 of x2 of t, if you take the Fourier series, then it is a1 x1 of k and a2 x2 of k. So x1 of t will convert to x1 of a, and x2 of t will convert to x2 of k. That's it. There it's simple. Then our second property, conjugation. So if you take a conjugate in time domain, x conjugate of t, then in frequency domain it will be x conjugate of minus k. Then scaling. So you scale it. So I told you, if you have a signal, you can scale it. Okay. So when you scale in time domain, your frequency domain will not alter. It remains as it is. So x of at is equal to x of k. Then we have time shifting property. So you shift in time domain, then what you have to do is you have to multiply that e power minus j omega k into t naught. So this t naught comes to the numerator, e power minus jk omega naught into t naught. So this t naught goes there. So x of k, this will be there, frequency domain. Again, you have to multiply by this exponential. So please remember this one. Then frequency shift. So what is this frequency shift? Like time domain shifting, I have the frequency domain shifting. So if I take x of t, t minus t naught here, okay, in the previous thing, here it is x of k minus k naught, because I'm shifting the frequency component. Then same thing, in the time domain, you have to multiply by e power plus here. There it was minus, here it is e power plus jk omega naught into t. Okay. The next thing, which is very important, so you have done convolution, right? X1 convolution of x2. So it is very difficult for us to do convolution in time domain, because you have to shift, you have to multiply, you have to rotate, and you have to take the area. So many things you will do. But if you convert this into Fourier series, it's just a multiplication of Fourier coefficients like x of k into x2 of k multiplied by time period t. So whatever the main inference what you have to get from this is, convolution in the time domain will give you multiplication in the frequency domain. So this property you'll be using in various things like control system or DSP, because we hate convolution, right? We want to do a simple multiplication. So what you have to do, you convert from time domain signal to frequency domain, and there you perform your easy multiplication there. Okay. So convolution is nothing but filtering. Okay. So filtering in time domain, it's easy if you multiply the same in frequency domain. Okay. Then what happens if you multiply in time domain? It's convolution in frequency domain. It's vice versa. That's it. Okay. So if you multiply two signals in time domain, then the corresponding in frequency domain, it will be convolution. Then what we have? We have time domain differentiation. So if you do differentiation for a signal, so d by dt of x of t, if you take them Fourier series, then you will get j omega k into x of k. So x of k will be as it is. You have to multiply by j omega into k. Then the final thing which is important, which is Parseval's theorem. According to Parseval's theorem, the left hand side, whatever you can see, this 1 by t integral 0 to t mod x of t the whole square dt. So the left hand side of the above equation is the average power of continuous time signal x of t, because mod x of t the whole square is there. So you are taking the average power of the signal, and the right hand side what you are getting, it is nothing but the summation of your Fourier coefficient. So if you want to get them average power of your continuous time signal, if you add and square your Fourier coefficient is more than enough. And the right hand side, whatever you are seeing is nothing but mod summation k is equal to minus infinity to infinity mod x of k the whole square is nothing but the power density spectrum of the signal. So this is nothing but power density spectrum of the signal. So this Parseval's theorem you will be using in most of the cases. So if you want to calculate the average power of the signal in time domain, so what you do, you convert it into frequency domain, get the coefficient, square it and add it. So that is the meaning of the Parseval relation. So this is maybe, I don't know whether it's there in the syllabus or not, but to be on a safer side, I have done these properties. Okay. So now we have done the properties. So let us solve some problems, and these problems you might have solved in mathematics, so it is easy for you guys. Okay, so make sure you do not miss this chapter. Okay, so before stepping into problems, let's see some some mathematical expression. Before, you have to know, I know you will, most of them will be knowing, but just a refresher thing for you. So e power j theta, how can you express? Cos theta plus j sin theta. If you want e power minus j theta, cos theta minus j sin theta. Then cos theta, how can you express? Half into e power j theta plus e power minus j theta. Then sin theta, how can you express? 1 by 2j into e power j theta minus e power minus j theta. So these things you have studied in mathematics. So these things you will be applying while solving the problems. So we need to have a look at this beforehand itself. So now we have seen the analysis equation, we have seen the continuous equation, and we have seen some properties. So let us dig into the problems. Okay, okay, so let me go to the first problem of today. So we have, first thing, we have to understand the question. Okay, be calm. Most of the things what you do is like, we do not answer, we do not understand the question itself. So the first thing what you have to do is sit calmly and understand the question. So first let us understand the question. So for the signal x of t is equal to sine omega naught of t, find the Fourier coefficients and draw its spectra. Okay, so what he has given? He has given the signal for you, and what he is saying? He is saying to find them Fourier coefficient and draw them spectra of the signal. Okay, so we will solve this slowly. So first we will write what is given. So Fourier coefficient means x of k, spectra means magnitude spectra and phase spectra. So I have explained you how to get the Fourier coefficient before itself. Then how to get the spectra? Magnitude spectra, root of a squared plus b squared. Phase spectra, tan inverse of b by a. So using those things, we will solve here. Okay, so we will go slowly. Okay, so we have the given signal as x of t is equal to sine omega naught of t. So what we are doing here, what we are learning, we are decomposing the signals into complex exponentials. So how can we write sine omega t as 1 by 2j e power j omega t minus e power minus j omega t. So sine theta, how can you write sine theta as 1 by 2j e power j into theta. Theta is omega naught into t minus e power minus j into omega naught into t. Okay, so just I have expressed sine in terms of exponential. Then what we have to do? We have to simplify. So let me multiply each term one by one. So sine omega naught of t is equal to 1 by 2j. You have e power j omega naught of t. Then we have minus 1 by 2j e power minus j omega naught of t. What I have done? I have just multiplied. Okay, now you see what I am writing here. We are comparing, we will take this as equation number 1. We will compare 1 with the equation x of t is equal to summation k varies from minus infinity to plus infinity x of k e power jk omega naught of t. So from where did I get this equation? So at the beginning of the class itself, I have written this as synthesis equation. So if you want to express your time domain signal in terms of frequency domain, how can you write? Summation k varies from minus infinity to infinity x of k e power jk omega naught of t. So we will compare this equation with the above equation and get the values of x of k. So how do we do that? So if you observe this, so let me take this bluing for you. So if you see this, you have 1 by 2j e power j omega naught of t, and you have minus 1 by 2j e power minus j omega naught of t. So now you have your expression x of k into e power jk omega naught of t. So whether this x of k e power jk omega naught of t, they have that similarity, right? So we can expand this one. So here this can be written as x of 1 e power j as it is. Your k value here is 1 omega naught of t, and this one as x of minus 1. Why minus 1? I will say you e power j of, here we have getting minus j omega naught of t, so I'll write minus 1 into omega naught of t. So what is your value of k? K is equal to 1 and k is equal to minus 1. So let us write now the value of x of 1 and x of minus 1. So we get x of 1 is equal to 1 by 2j. Compare this one. So only I have written this one for you not to be confused. Then x of minus 1 is equal to minus 1 by 2j. Okay. Now also x of k is equal to 0 for k not equal to plus or minus 1. So except this plus or minus 1, all the values of x of k is equal to 0. That's it. Okay. So we have got two coefficient x at 1 and x of minus 1, and our first problem gets over. So we have found the Fourier coefficients. Then what else do we want from here? We want the spectra. So we want the magnitude spectra and we want the phase spectra. So I told you your x of k. How can you write this x of k? Root of a squared plus b squared. So this I have written there. So how do you calculate the magnitude? So if you consider this x of 1, so how you have, so this expression magnitude of x of k is equal to root of a squared k plus b squared k. So for which expression I have wrote? I have written for a plus jb. So your Fourier coefficient should be in terms of a plus jb. But what have we got here? We have got x of 1 is equal to 0 plus 1 by 2j. But you should get in terms of plus jb. So j should be in the numerator, but here you can see j in the denominator. So what will I do is just observe x of 1 is equal to 0. I will take the j to the top, then it becomes minus. So x of 1 is equal to 0 minus half into j. So I'm just expressing in terms of a plus or a plus jb. Okay. So you have a plus j, your b is minus half. So x of 1 I have represented like that. Similarly, what we want x of minus 1. So x of minus 1 is equal to 0 minus 1 by 2j. You can bring that up, then you will get plus half into j. So because I want in terms of a plus jb, so I am bringing this j to the top. When you bring the j to the top, your sign will get changed because 1 by j is equal to minus j. So using that analogy, I have written this x of 1 and x of minus 1. So now we know what is a and what is b. We can get them magnitude spectra and also the phase spectra. So let me take you to next sheet so that we can do their aram se. Okay. So yeah, add to the new page. So now we know x of 1 and we know the x of minus 1. In terms of a plus jb, we have expressed it. So now let me write them magnitude spectra. So first one, magnitude spectra. So let me, use a reading for that. So magnitude spectra, how can we get? Magnitude of x of k is equal to root of a squared plus b squared. So you want magnitude at x at 1. What is your value of a? 0 whole squared. What is your value of b? Minus half the whole squared. So you will get x of magnitude of x of 1 is equal to half. Then what we want? Magnitude of x of minus 1. So 0 a squared plus what is your b here? Half. So half squared. So what is your magnitude? Again it is also half. Then what do we want? We want them face. So how do we get the face? I told you the formula. Face we will get as tan inverse of p by a. So let me calculate the face for x of 1. Let me calculate the face of x of minus 1. So let us calculate first angle of x of 1, which is equal to tan inverse of b. What is our value of b? Minus half. What is your value of a? 0. So this will be equal to tan inverse of minus infinity, which is equal to minus pi by 2. Now what we want, the second thing we have to do, we want the angle of x of minus 1. So this is equal to tan inverse of b by a. So b is half, a is 0. So tan inverse of infinity, which is equal to pi by 2. So now we have got the magnitude and now we have got the phase, and what is left to do? We have to plot it. So let me plot it. Okay. So first I'll plot the magnitude spectra. So take your x-axis here. Then you have at 1 and minus 1. So your value at 1 and minus 1, it is half. So this is the values of k. So this is 0. At 1 you have and at minus 1 you have. So what is the value? Half and half. So write this one half and this one as half. So this is your magnitude spectra. Now we want phase spectra. How do we get the phase spectrum? So we have got the angle, we just have to plot it. So take your 1 minute, let me use a straight line for that. So this is your k axis. Okay. So at 1 and minus 1 we have. So at x of 1 angle is minus pi by 2. So this is minus pi by 2. And x of minus 1 you have as plus pi by 2. So this is plus pi by 2. Okay. So this is how you get your magnitude spectra and phase spectra. Okay. Now using the same concept, let me solve another problem and wrap up for today. So let us see what we have done here in this problem, so that it will be helpful for us to solve the next problem. So we have our signal x of t is equal to sine omega naught t. Then I have expressed in terms of exponential. Why did I express in terms of exponential? I have to express in terms of the synthesis equation, so that I get the values of x of 1 and x of minus 1, or any other thing, any other coefficient I would have got easily. Then what did I do? For magnitude spectra, magnitude of x of k is equal to root of a squared plus b squared. Angle is equal to tan inverse of b by a. Then using that I have plotted it. Okay. So now let me take you to another example. So what we have to do is, like, we have to solve different kinds of problems. There is no need, there is no point in solving, like, if I could have taken the second problem as cos and I would have done. So I do not like that. So if I solve different kinds of problem, you will also get an idea. Okay. So now let us find the Fourier coefficient and draw the spectra. So the question is the same. Okay, so no need to understand the question again because the question is the same. You have to find the Fourier coefficient and draw them spectra. So what is your signal given here? X of t is equal to sine 2 pi t plus cos 3 pi t. Okay, so another cos term is added. So there is a slight twist here. So observe what I am doing. So we have the given signal x of t is equal to, so sine 2 pi t plus cos 3 pi t. So this is our given signal. So if you observe, the first signal has an angular frequency of 2 pi. So this is your angular frequency, and your second signal has an angular frequency of 3 pi. So in order to solve this, so to get them angular frequency omega naught, so you should take them GCD of these two. So omega naught is equal to GCD of 2 pi comma 3 pi. So what is the GCD of 2 comma 3? Sorry, 2 pi comma 3 pi, which is equal to pi. So your greatest common divisor is nothing but your angular frequency, which is equal to pi. So this thing you have to remember. Then other things remains the same. So let us solve. So we have got our signal x of t is equal to sine 2 pi t plus cos 3 pi t. So what we have to do? We have to express in terms of exponential. So how can I express sine? 1 by 2j e power j 2 pi t minus e power minus j 2 pi t plus 1 by 2 into e power j into 3 pi t plus e power minus 3j pi t. Okay. Then what we have to do? We have to multiply each and every term inside to get an Fourier coefficient, and then we can compare. So 1 by 2j e power j into 2 pi t minus 1 by 2j e power minus j 2 pi t plus half e power j3 pi t. I'm just multiplying. Okay, there is nothing big rocket science going on here. Plus half e power minus 3j pi t. Okay, so now what I have to do? I have to compare with them expression, which is our analysis equation. So let me take this to next page so that we will not have any confusion. So add to new page. Okay, so I have my expression here. So we have to compare with the analysis equation. So what is our analysis equation? X of t is equal to summation k varies from minus infinity to infinity x of k e power jk omega naught of t. So how did we do the last sum? Similarly, we have to do this particular sum. Okay, so what we have got k value as here 2, k here it has minus 2. So observe this one and write first only. Then here it is k is equal to 3, and for this one k is equal to minus 3. Okay, so that time your confusion will go. So e power something pi t is there, so that is your value of k. So k is equal to 2, k is equal to minus 2, k is equal to 3 and minus 3. So we have total of 4 coefficient. So let us write each one by one. So x of 2, what is the value here? 1 by 2j. Okay, then x of minus 2, what is the value? Minus 1 by 2j. Then x of 3, which is equal to half, and x of minus 3 is equal to, again it is equal to half. So then what we have to write? And x of k is equal to 0 for k not equal to plus or minus 2 and plus or minus 3. So this one you can write it separately. So now we have got our first thing, your Fourier coefficient. So you have got your 4 Fourier coefficient. Then what we have to do? We have to plot our magnitude spectra and phase spectra. So let me first, write them magnitude spectra. So magnitude spectra, as I told you before, how we have to express x of k in terms of a plus jb. So we will take x of 2. Let me express that in terms of a plus jb. So we have 0 plus 1 by 2j. So j goes to top, it becomes 0 minus 1 by 2j. So first thing you express in terms of, j terms, so that your life will become easy. So 0 minus 1 by 2j. Okay. Then what we have got, x of minus 2. So x of minus 2 is 0 minus 1 by 2j. So take the j to the top, it will become minus j. Minus j into minus 1 will be plus j. So 0 plus 1 by 2 into j. Okay. So if you write this one, it's enough. For x of 3, no need, because there is no j term, right? Only a term is there. So x of 3 you can write here if you want. Half plus 0j. Then x of minus 3 is equal to half plus 0j. Just, for your life to become easy. So what is your magnitude? So magnitude of x of k is equal to root of a squared plus b squared. So let us write the magnitude spectra for x of 2. Root of, what is your a? A is 0. What is your b? B is minus half. So minus half the whole square. Again you will get answer as half. Second one, x of minus 2. So what is the magnitude? 0 square plus half square. Why half square? Your a is 0, b is half for x of minus 2. So again you will get half. Then what do we want? X of 3 and minus 3. X of 3 is equal to root of, here you see only half square plus 0 square again. Again it is half. And for x of 4, what do we have got? X of 4 is equal to, so again it is half square plus, sorry, x of minus 3. When I'm saying x of 4, it is wrong, because we have x of 2, we have x of minus 2, we have x of 3 and x of minus 3. Okay. So usually you write like 1, 2, 3, 4. So it came in a flow. Sorry for that. Okay. So again you will get as half. So we have finished the magnitude spectra. So in order to calculate the phase spectrum, let me take this magnitude spectra to the next page. So let me take to the new page. So we have our magnitude spectra at the top. So let me write the phase spectra here. So what is our phase spectrum? Phase, first one, angle of x of 2, which is equal to tan inverse of b by a. So what is b? Minus half divided by 0, which is equal to, similarly like as previous, it is minus pi by 2. Then we want angle of x of minus 2, which is equal to tan inverse of 1 by 2 divided by 0, which is equal to pi by 2. So this is similar. I did not elaborate on that. Then angle of x of 3, tan inverse of, here b is 0 and your a, let it be anything, it will be 0. Then what have you got at the last? X of minus 3, again it is tan inverse of 0 by half, which is 0. So we have got our magnitude, we have got our angle. So what is left is we have to plot it. So let me plot them, magnitude spectra and phase spectra. So first here I'll plot the magnitude spectra for you guys. So yeah, so we have 2, minus 2, 3 and minus 3. So what is your x-axis here? came. So what are the values you want to plot? 0, 2, 3 and -2 and -3. Okay. So what is your value at x of 2, -2, 3 and -3? All the values are equal to half. So let me plot this. All the values equal to half. So you get all the values equal to half. So this is your magnitude spectra. So this is your magnitude spectra. So in order to get the phase spectra, what we have to do? Again the same logic. First write the x-axis, then you plot it. So we have our x-axis as came. So we want the value at 2, 3 and -2 and -3. So what is the value of 2? Angle of x of 2 is minus pi by 2. So here minus pi by 2 and x of -2 it is plus pi by 2. So it is plus pi by 2. Then x of 3 is 0 and x of -3 is 0. So no need to plot for that one. So this is your phase spectra. In textbook, they will give you directly this phase spectra and amplitude spectra, but you might be wondering from where it has come. So you follow my notes, you'll get this one. So this, how do you get this phase spectra and magnitude spectra? So let me wind up for today. I think thank you for cooperation. Okay. So thank you guys. Okay. If you have any doubts, you can mail me. Okay.